I'll talk about supercoset sigma models and mostly about conformal supercoset sigma models. So let me before I forget, I should mention my collaborators. So most of the results I'm going to talk about are based on two papers within the last year with Konstantin Kandu, who is a postdoc at ETH, and Vladimir Mitev, who is a postdoc at Humboldt University in Berlin. And so there were two papers, which I guess I have the numbers somewhere, but not here. And then I will, time permitting, I will talk about some unpublished results or work in progress with Václav Klapak, who is a PhD student at DESY, and Alexander Cagnazzo. Okay, but in terms of the actual results, it's sort of the first. And then I should say that it's part of a long-term project. And so there were a bunch of other people involved in the past, who I should also mention. That's Thomas Kreutzig, also Thomas Queller, and Hubert Soler. Okay, so I guess I got them all. Maybe. So. Yeah, so the topic, of course, of this meeting is gauge theory and integrability. And of course, one may wonder about the relation with this, with my talk. What? Good, yeah. So there's some connection, of course. Sigma models for a long time were treated in two dimensions as sort of a toy model of gauge theories. And the sigma models I'm going to talk about have vanishing beta function, have families, one parameter families with vanishing beta functions. So in that sense, you could think of it as a toy model of, let's say, n equals 4. And of course, they're all integrable, at least classically, and most of them they are probably also integrable quantum mechanics, and the quantum theory. So in my kind of wildest and most optimistic scientific dreams, I see many other relations to gauge theory, mostly going through large n-gauge theory and ADS-CFT correspondence. And if I warm up sufficiently during this talk, I'll tell you about this at the end. But to be honest, I think you should kind of view this talk as a talk on two-dimensional conformal field theory. But there's one unusual feature of all these models I'm going to talk about. They're all non-unitary. So most of them will have central charge 0 or central charge negative. And you might say, well, why should I bother? Or this is probably a nasty subject. And it's true, it's a nasty subject for the following reason. In these models, the central charge is not a good measure for the number of degrees of freedom in the system. Because central charge 0 is 0 because there's usually huge cancellation between positive and negative central charges. And so we know almost nothing about RG flows in these theories because we have no C theorem. And so this is actually in all the applications, it's sort of a stumbling block that you can't really, you don't really know what the IR properties are, what the IR fixed points are. You can't really identify them, even if you know a good microscopic description of the system you want to study. And so this makes these theories typically very difficult. And so they are difficult, mostly because of that. So many of the techniques, when you think about it, that we use to study dualities are based on a good control of our RG flows. And so if you don't have that, you're kind of lost from the beginning. On the other hand, they're kind of quite relevant. I mean, I guess for people working in condensed matter, they know that C equals 0 theories appear all the time when you study systems of random disorder, like quantum Hall effect and things like that. For string theorists, in fact, it's also kind of known because ultimately all string theory models are built on the worldsheet from C equals 0 conformal field theories. The only reason why we usually don't bother about non-unitarity is that the standard models that we use, for instance, to describe strings in flat space or Calabi-Yau compactification, they have a unitary complicated matter sector of C equals 15 and then a free ghost sector of C equal minus 15. And so the cancellation, of course, is to C equals 0, but the non-unitarity we can easily treat because it's in a free sector, in the free ghost sector. But string theory models of sort of modern string compactifications, like ADS 5 cross S5, are not of this type. You can actually not automatically separate the matter sector, sort of these models into a unitary matter sector, a non-unitary ghost sector. So one example is this, well, string theory, of course, for ADS 5 process 5. So you all know that ADS 5 process 5 has this coset description. I believe you all know. If not, then so the bosonic base of this space is this coset space. And so there exist nice models to build string theory, and there in particular Berkowitz developed this sort of pure spinor description of these models. And if you look at that, then even sort of what you would call the matter sector, the sigma model on this part is non-unitary and interacting, of course. Then the ghost sector, these pure spinor ghosts are also they are non-unitary, and then they interact even with each other. And so there's no way to disensemble sort of the non-unitarity from the interaction, okay? Unlike, as I said, things in flat space. So I hope that's sort of enough motivation to survive the next hour and to understand that it might be relevant to talk about non-unitary theories because...
in string theory we also have the selection principle that we don't keep all the states.
Yes, of course, that's true. So in the end, there will be also in this model, of course, even though it's the worldsheet model is based on a pure spinor string, has a non-unitarity built in. Of course, there's a BRST operator, and sort of a good BRST operator should in the end leave a unitary spectrum, right? So that's sort of the art of building a string theory, is of course there's a lot in this choice of this BRST operator. But still in intermediate states, if you want to compute amplitudes, you will see all these propagating. I mean, if you build a theory, you will see the non-unitarity. But it's true, of course, ultimately, and in some examples it has been demonstrated very explicitly how then these BRST operators indeed in the end just leave a unitary spectrum. But for all properties that have to do with consistent building of these models, that happens kind of before you go to study equimology, right?
The question is about the condensed matter applications.
Yes.
Is there also a principle which
No, in that case, I mean, okay, so normally in these models, then not all operators would be interesting observables. But so you know more or less from the problem which operators are the ones that have interesting physical applications, right? So, okay. So, so any other questions on my motivation? So this is all I'm going to tell you about motivation. And again, so you have to survive one talk of this non-unitary control field theory. There's no more question. Let me give you the outline. I'll basically talk about two results that we obtained on the spectrum of these theories, and then some applications. So we'll start with, well, maybe I don't have to write this down. So I'll first talk about sigma models as a given in title. So I'll give you a result on the coset space sigma models, and we'll compute the entire one-loop spectrum for all conformal cosets, in fact, all coset symmetric space coset sigma models. Then I'll kind of switch a little bit gears. I kind of seemingly go outside the scope of this talk. I'll talk about Westermino models, arguing that somehow it's not really good to just restrict to the class of sigma models. I'll give you also a nice result on the spectrum of Westermino, deformed Westermino models, and then I'll try to tie these things together by talking about some dualities that I think are interesting. Okay, so if there are no more questions, let's start with the first part. So this is coset sigma models. And of course, the most famous sigma model, coset sigma model, or sigma model that you know, a nonlinear sigma model is the ON model, ON vector model, right? Everybody knows what it looks like. So if I write down the action, it has a coupling constant, which I call 1 over r squared. No, sorry, r squared, of course. And then, so it's a two-dimensional model, and the action is something like this, just like this, but then I have a nonlinear constraint. This would be free field theory, and so I want x squared to be equal to 1. Okay, so that's a nonlinear sigma model. Now, so this would be ON models if x takes values in Rn. And now we just generalize that and make it super. So to make it super, I assume that the X actually takes values in R m to n. Okay, so this means m is bosonic dimension, and I have 2n, an even number of fermionic directions. And I impose a constraint, which is the analog of this. I have to do something with the fermions as well. So I impose the constraint that, well, all the bosonic ones, we call them xa squared. Okay, let me make it a matrix notation. Xa xb times eta ab is equal to 1, where eta ab is diagonal matrix, almost diagonal, which has a bunch of ones along the diagonal. So it's identity matrix in the first m components. That's then kind of just a sphere constraint. And you put like 0, 1, minus 1 in the last 2m direct in the fermionic directions. Okay. So that means that you have, I mean, this is a well-defined space in the sense that you have an algebra of quantities that lives on this thing. You have the freely generated algebras generated by the bosonic, m bosonic coordinates, and 2n fermionic coordinates, and then you impose this as a, well, the ideal generated by this thing you divide by. So that's a well-defined non-commutative algebra, and that defines sort of the space in many ways of thinking. Okay. So I'll talk. I mean, so this is. So you can see by analogy. So of course, if this was just purely bosonic, this would define a sphere, right? So if n was equal to m was equal to 4, and n was 0, then would be the O3 model. So O4 model, which is a 3-sphere. And so here it will be an SO m to n. Sorry, m minus 1 to n. So it's a sphere with fermionic directions attached to it. And you can also write it as a coset, like the O4 sigma S3 is O4 divided by O3. So similar, you have here that this is OSP, OSP, what is it? M to n divided by OSP m minus 1 to n. Okay, so that's many different ways of thinking about the space. So it's a coset space. It is a sphere with fermionic directions. So of course, in this parameterization, I mean, the action looks simple because we have too many fields in the theory, right? There's m bosonic fields and sorry, I'm always getting, m bosonic fields and 2n fermionic fields. But of course, you can, in principle, try to solve this constraint through m minus 1 bosonic fields and 2n fermionic fields and write out the action just in terms of those fields. And then what you will get is sort of another way of writing a sigma model.
Use the same eta matrix to define the action?
Yeah, so sorry, yeah, that's the same. That is, yeah. So if you do that, I mean, I'll do this only for you just once for the case that m is equal to 4 and n is equal to 1. So that's then sort of the OSP42 sigma model. So then you start with 4 bosonic fields and 2 fermionic fields, but you eliminate through the constraint one of the bosonic fields. You end up with 3 bosonic fields and 2 fermionic fields. 3 bosonic fields are some kind of parameterizing in the sphere, so they are angles. And the action that you get, if you do that,
does it project onto some bosonic manifold, or it's not?
Does it project into some bosonic manifold?
So the usual sphere is some manifold there, right?
The usual sphere is a submanifold, yeah.
There's no obvious projection.
In this case, I don't quite recall. I can probably check, but I don't. So when you write down this in terms of these fields, let me call the bosonic fields phi, phi1, phi2, phi3, because they're angles parameterizing the 3-sphere, and fermionic fields psi maybe. Then you get, can write the answer, of course, in, well, I mean, so what do you get? So this is for m equal 4, n equal 1. You get a model, okay, I approximately will get that right, okay? So this is, So minus signs and factors of 2u. I'm a bit cavalier with it. Yeah, any terms that I didn't actually write. So this is what it looks like. It looks pretty ugly, right? But of course, it's ugly because the metric on our space is complicated. You can write that, of course, in this form: r squared d2z g ij of phi, where this phi contains phi 1, phi 2, phi 3, and xi 1 and xi 2, and then d phi I d bar phi I. Here.
Line.
Oh yeah, I mean had that
Psi
too.
is a scalar, right? Psi is a scalar.
Psi is scalar in which sense? Oh, so it's a world sheet. Yeah, it's a fermion with dimension 0 fermion. Yeah. Okay. Yeah, sorry. Yeah, that's my problem too. But no, at least I wrote this down properly. I told you that.
So you're getting always the action which is second order by fermionic modes as well, yeah?
I think.
I was confused.
Yeah.
And say for this ADS5 as 5 example, you will also get something.
No. This will be. So I mean, this is also. I mean, so quadratic and fermion. I mean, this is fourth order.
Quadratic and derivative, so it's not.
Oh yeah, quadratic and. Yeah. This is. I mean, this is a normal sigma model. Yeah. So it's quadratic and the. So it can be written into this form with this, where this is a. So and of course the metric is complicated, and you can read off from here sort of this complicated metric. So one of the reasons I wanted to show you this is to kind of make very concrete. This is the kind of models I will be talking about. You see, they're very complicated non-interacting theories, right? There's a lot of nonlinearity in this model, and of course you can think of it as in terms of this. In fact, there's another way of writing it. You see also in supergeometry, you can take the metric and write it in terms of field bind, split it into a product. So you can write this as E I alpha phi E j alpha phi, where E is sort of the field bind, and then alpha contraction is with the killing form of your symmetry algebra. And then you can actually introduce a new field J, which is J alpha, which is sort of I alpha d phi I, something like this. Okay, and then of course the action looks again very simple, but of course this is just J alpha, J alpha. Okay.
Alpha runs through.
Alpha runs. Okay, I should say that. So alpha runs through indices in kind of in tangent space at the origin. Or you say, so here we have a sigma model. So we have two groups involved. Maybe let's already switch to that description. So we have a group G and a group H, or Lie algebra, Lie superalgebra G and H. And so we can build G mod H. Let's call that space M. This is sort of, I mean, whatever is in G but not in M. And that's a representation space for H, of course, for the thing that I divide by. And so this index alpha should be thought of as an index parameterizing basis elements in this M. Okay. So you see, so these JA have kind of an H charge. They transform non-trivially under H, but of course it's contracted over H. So this is a H invariant object, as it has to be in a theory that describes, well, a quotient. Everything has to be H invariant, but the J itself is not really observable in the theory. It's just built in. So you see, again, the action looks very complicated, very easy, but of course that's because all the nonlinearity has been moved into this formula for the current, for this J. So this will become important at some point, so that's why I wanted to go. So now the issue of conformality. So you can take these models. In fact, I mean, these models that I wrote down here, and then generalize that to more general coset spaces, G mod H. And you can start computing the beta functions for these theories and try to find cases with, where the beta function vanishes. For this example here, it turns out that beta function vanishes if and only if m is equal to 2n plus 2. Okay? So in that case, beta function vanishes. And then you kind of can start to scan other cosets, because once you're warmed up, it's not so difficult to look through the rest. And I just gave you the result of that on this magic blackboard. So that's the list that you find. Okay, so that's the list of all the sigma models that you can build that have where the sigma model coupling doesn't run. Okay. Nikita has a question on.
Yes, it's just a question from the audience.
Yeah.
What looks like P exactly?
Oh, what looks like P is actually an M. Yeah, I guess I should.
M was just a bosonic part. So.
Well, M is just a boson. Yeah. This is also this P is an M and things like that. Right.
So what about the case n equals to 0? Okay, so it's you want
N equal to 0 is actually, that's a famous one. That's just a free boson, compactified free boson. That, of course, we all know. So all these theories have central charge equal to 1 for any n, actually. So I told you that most of the models I talk about is C equals 0, but this is an exception. Here's the family with C equal 1. But you see that the C equal 1 is because of a cancellation. There's, of course, a bosonic part, which is just a sphere sigma model that has C equal 3 in some sense. And then there's these fermions, symplectic fermions, they contribute C equal minus 2, and the sum of these is C equal 1. So you see already that the real sort of degrees of freedom in the system are much more than the C equal 1 would suggest.
And in all cases you have logarithmic conformal theory?
Yeah, they are all logarithmic except maybe for a few. Yeah, I think it's safe to assume that they're all logarithmic. I mean, in the non-unitary world, not having logarithms is sort of an accident that it's very difficult to get, right? If you're interested in that aspect, I mean, there's various points where I'm hiding logarithms somehow, where I can say a little bit about those, but I don't want to kind of make things too complicated. So that's a list, okay? So you just stare at it once. What you notice is that the numerator group is always one of the groups always P2n plus 2 to n, or PSUNN, or D1 to alpha. That's actually necessary for the vanishing of one loop beta function. And then, so the denominators have extra constraints coming from higher loop beta function in this case. So you see there's real Grassmannian superspaces, complex Grassmannian superspaces, and then this family, this gives C equal 1, C equal minus 2, C equal minus 2. Then you can also start introducing worldsheet supersymmetry. And in fact, the second line here is models where you have put like a n equal 1 worldsheet supersymmetry, and which got enhanced to an n equals 2, because these are, if you look at it, they are all Hermitian symmetric superspaces. And so for these Hermitian symmetric superspaces, you also get have no running of the sigma model coupling. So you get like one particular choice of this type, sort of real Grassmannian. Then of course the most important family is this. This is complex Grassmannian superspaces. So CPN models, or the supersymmetric versions, would be in here, CP34 in particular, and so on. And you see here on this side, you see that's all C equals 0 or C negative. So these are definitely okay. So I just wanted to flash that list once. So all I'm going to say is on all these models, okay, at the same time. And so by now we have some results that really apply to all these theories. Okay, so that was the introduction to sigma models. Any questions on that?
So the AS5 versus 5 example is not on the list.
That's not on the list. Sorry, I should say when we scanned this list, we only scanned symmetric superspaces. And so we made the assumption that the numerator is actually fixed under a Z2 involution. And that has certain technical simplifications. I think for some of the things maybe I can talk about is also not really essential, but you just need to work harder to get the Z4 included. Okay. Of course, sorry, I should for people. So in this case, the denominator is fixed under Z4, acting on the numerator. So this is not a symmetric space, it's some kind of generalized symmetric space. And in fact, all examples that are known in string theory, I think, of this out of this Z4 type. So in principle, we are slightly out of this rim. I think there's a slightly more serious issue about why things that I'm going to talk about are not directly applicable to this case. In this case, also the denominator group is non-compact. And you will see at some point some of my results actually assume that the denominator is compact. So that I think requires a little bit more work to go to. The numerator non-compact is not such a big issue, but the denominator, I'll maybe, if I have time, I'll point out where you have to work more in order to get to. But so there's two examples, two cases, two things, features of the string models that are not in this class. That's the fact that here it's a Z4 and that the denominator is not compact. I mean, but anyway, I think both things can be addressed, but the results I'm going to show you are not directly applicable to that case. Any other questions?
Sir, and
yeah.
About coupling, you said that it's not running.
Yes.
So it's in all these cases.
Yes, in all these cases, yeah.
Very essential,
Yeah, I mean, this is essential, yeah. So, I mean, okay, so in some sense, the formula I'm going to show you for the one-loop sigma model doesn't really assume that. I mean, it's actually valid, the formula, with some very small modifications, even when the coupling runs. But for my thinking and the punchline of this talk, it's important that it doesn't run. So I'll mostly consider just the conformal cases. Of course, I mean, so many of these models are, sorry, these of course not, but many, I mean, in this family, for instance, you have many asymptotically free sigma models, right, where the coupling runs, but they are asymptotically free. As m is larger than 2n plus 2, larger or equal, then you will have asymptotic freedom. Okay.
Is it this coupling isn't running non-perturbatively too? Because if we substitute n equals 0, we obtain O2 the sigma model, and we know that it could be there could be some non-trivial effects in the sigma model.
O2 is U1, that's a free boson. There's nothing that can.
But it has phase transition. Phase transition.
It has what? Oh, I see. Yes, okay, so that's. I mean, anyway, so here there's no source perturbative or non-perturbative beta function. It's just.
Well, the question is that maybe about non-perturbative you simply don't know. You know for sure that perturbatively it's not running, but as in this case.
No, I mean, I think.
Yeah,
I think I have another argument that shows that it's
that's forbidden.
That's forbidden, yeah. So we can talk about this maybe after. Okay, so I wanted to start in these models to kind of show you the first result, namely on the spectrum. And let's see whether I can efficiently erase that. Okay, so I want to talk about the one-loop spectrum of these theories. And first of all, we have to, of course, talk about the observables. So what I mean by spectrum is sort of the spectrum of anomalous dimensions of local operators in the theory. And so again, these are conformal field theories. So they have, well, once you switch on the coupling, of course, they develop some kind of anomalous dimension, all the operators, and that's what we want to compute, okay? So first we have to talk about the space of operators, of course. I mean, what kind of operators can I have? And you remember probably from the free boson, that's an easy way to do this. You have, of course, these famous exponentials, e to the ikx, okay? And then you have like these tails of derivatives of the bosonic field. So dx, d squared x, and d bar x, d bar squared x, and so on and so forth. So in fact, for sigma models, there's a generalization of that. The only difference is that, of course, the U1 model, there's no denominator. The denominator is trivial, so nothing carries charges with respect to the denominator. Whereas in the G mod H model, there's, of course, you build easily objects that have a charge with respect to the denominator, which you have to cancel. So we saw one such object already here. This was this this object J, which I pointed out had a charge with respect to H. So of course this will also play an important role in the construction of general fields. So you have to try to kind of make the physical fields of a theory, of course, chargeless. So the general formula for the field, so fields have a number of quantum numbers. I mean, several quantum numbers. So fields are on the world sheet. They have fields, so I couldn't consider, I guess we learned this is a point like figure observables, I guess, according to yesterday's first talk. So the lambda here is a vector consisting of a weight of G and then 3 weights of the denominator group H. Okay, so this is a representation of G, and these label representations of H, the algebra of the denominator. And so, so what you have is basically, so like in, okay, so let me just put this here, IKX and then dx, so some function of dx, and some function of d bar x, d bar squared x. So this is a general form. So of course the dx will be now replaced by these j's here and derivatives of those guys. So I'll have here p, and that depends on j and dj and so on and so forth. And since this thing is charged, of course this object that you think of some kind of polynomial will be typically charged. And so by some kind of projection, we assume that we build something that sits in some definite representation of the H group. So if we have just J, for instance, this could be just the representation M, but then of course you can build up other representations. So we have a similar thing for J bar, D bar, J bar. So, so this carries charges. So these are 2 of these labels here. So then we have to, well, actually we, okay, so then we have to talk about, so this is this part. We have to talk about a zero mode piece. Zero mode piece I denote by V lambda lambda of ZZ bar. I'll tell you in a moment what that is. And then we have to make it uncharged under H. So there must be some kind of Clebsch-Gordon coefficient that, that projects us to something that transforms trivially under H. Now, what's this V lambda lambda? So in the free boson, this is just a Fourier mode basically on U1. Okay, so in the more general case, this would be, well, not quite a function on the coset space, but it's a section of a homogeneous vector bundle, of course. So V lambda lambda is a section in homogeneous vector bundle on G mod H. And concretely, so in homogeneous vector bundle, of course, you have to have different homogeneous vector bundles. They're like labeled by the fiber. The fiber of these things is in a representation of H. So you have, in order to describe them, you have to fix a representation of H. That's this H lambda. And so very concretely, you can think of these objects as functions on G with certain periodicity properties. So it's a function of G that takes values in a finite dimensional representation, let's say, of H. And it's H covariant. So it has H is equal to D lambda. So there's a representation matrix in that particular representation that you picked, H minus 1 S of G. So these are kind of quasi-periodic functions on G mod H. So these things you can classify, okay? So and again, so this is particularly simple for compact G and compact H. You can very easily write down, like count the options that you have. So these are the things that correspond to this. There's a generalization of the Fourier modes up there. And of course, these also carry charge with respect to H, right? Because the fibers transform non-trivially in H. And so you have to make sure, again, that the object, the observable of your theory, is uncharged under H.
Excuse me.
Yeah.
Why that your current G is holomorphic?
No, it won't be holomorphic, but the counting of for the counting of states, this gives all the possible fields in the theory. But it's not holomorphic. No, I mean, No, the current, I mean, so the current will have a good...
The analogy that for free boson, we just know that everything
Yes.
can be constructed from this holomorphic conserved currents and exponentials. But so what is left in non-trivial situation? Why you just write down immediately in the same spirit this polynomial, if this is not clear?
No, I mean, it's kind of clear. So what are we counting, basically? I mean, it's just a rewriting of that counting. So we could talk a little bit more about this. And of course, I mean, we didn't write it down like that. But I thought it was probably we were just not smart enough. We could have written it down like that. So, of course, what we are counting is basically all the derivative fields we can write down on this G mod H theory, right? So we are counting basically everything we can build from zero modes and then applying derivatives. Now, then, of course, when you think of it like this, so zero modes are kind of this piece here, and then applying derivatives, d and d bar should give all operators. But it's very difficult in that description to understand which, I mean, like equalities between fields, because when you start acting with derivatives, you will start getting lots of different representation of the same field. So it's very difficult for counting, but it's basically what happens here. So I'm just saying that these data sort of give a one-to-one counting of all the fields. Again, we could talk about this in more detail, but
the question is,
yeah.
Since this is going to be a conformal theory,
Yes.
what can you say about the holomorphic factorization? So what is
No holomorphic factorization. No holomorphic factorization. I mean, of course, there's t and t bar, and it's conformal, so we have holomorphic t and holomorphic t bar, but of course, beyond that, you can even see in many examples, I mean, that they're intertwined. Because, again, they are logarithmic, brings us back to this question before. Logarithmic theories cannot, by construction, have a holomorphic factorization, because that would be in contradiction with logarithmic and locality. So they have no holomorphic factorization. So you cannot deal with these theories with the standard technology of like chiral objects and representation theory. This is just not possible. Okay? So yeah, so it looks very complicated. Still, I claim that these theories are important enough to think of ways of replacing that. Good. Okay, so now we wrote the fields, and I'm supposed to write formulas for anomalous dimensions, one loop anomalous dimensions. And again, so in fact, there's quite a bit of literature on conformal dimensions, anomalous dimensions in sigma models. I think in particular in condensed matter side, they computed them. In fact, for these kind of zero mode pieces, I think there's results up to 4 loops for ON models and things like this. There's also for certain cases, some results on operators with derivatives. But in fact, because people in the past, in particular in condensed matter theory, they usually use this other description where they kind of build operators by zero modes and derivatives thereof. It was very difficult to kind of get universal results. So here we have two pieces. So to the anomalous, there's 2 contributions to the anomalous dimension, which are kind of a slightly different type. There's one that is the anomalous dimension of this kind of zero mode piece, and that you can compute. And of course, it's not so surprising what the outcome is. You will find that the change of dimension. So again, I mean, naively, of course, the dimension at zero sigma model coupling or infinite radius is, of course, just given by counting the number of derivatives. Okay, so it's very easy because it's just naive dimensions. And so what I'm writing here, this delta thing would be the change of dimension as you go away. So for the zero mode piece, the dimension at infinite, there's no derivatives in there, so there's dimension 0. And once you go away, they will acquire an anomalous dimension. And this anomalous dimension for the zero mode, the zero mode depends, of course, on lambda and lambda, is given by 1 over r squared times the Casimir of G in the representation lambda minus the Casimir of G in representation lambda. And this combination of Casimirs is, of course, famous. I guess that's the eigenvalue of the Bochner Laplacian in this homogeneous vector bundle. So it's not so surprising that this is sort of the one loop answer. So when you compute the contribution to the anomalous dimension of the tail, Okay, so you actually see that it's computed by some kind of spin-spin interaction. You can think of these J's and derivatives of J as kind of spins, and when you derive the formula, you get some formula for spin-spin interaction. You can write that. So this will depend, of course, on mu and mu bar and lambda. So the tail is this, and the head is that, zero mode. So here you get 1 over r squared, and then you get Casimir lambda g, quadratic Casimir minus Casimir mu g minus Casimir mu bar g. And when you add these two things up, you get the final result for the one-loop anomalous dimension in the sigma model. That all depends, of course, on all the quantum numbers. And it will be, in fact, so you see that, I guess I didn't get that right. No, I did get it right. So you see this thing cancels against that, and you just get Casimir lambda g minus, sorry, Casimir. Okay, so that's the formula for the one-loop anomalous dimension.
Is it possible to represent it as a staging value of some Hamiltonian, like a spin chain?
As I said, I mean, this looks a little bit like, it's not really a spin chain. I mean, it looks like more like a system of spin atoms which have like just pairwise interaction. This piece, and then this is, so I don't know of any other way. Of course, yeah, it would be, at some point I thought like, yeah, in four-dimensional gauge theory, so we have, yeah, it doesn't seem to be quite of the same type here, so there's no natural ordering somehow of the, so it's somewhat similar, but yeah, I don't have anything very, very smart to say about it, but I would say it's actually not quite of this type, but it has some similarity with that. So this piece here has some similarity. The zero mode piece, I don't know. This is just a geometric part of the answer. Okay, so this is the answer. Maybe do I have time for a detour or not?
So,
not really, but
so,
yeah.
Mu and mu bar representations of H.
Yes. Oh, sorry. Yeah. Thank you. Thank you. So that's the correct formula.
But,
Oh, sorry, and that's also.
then what about the G lambda? Capital lambda is a representation of G, but it can also be a representation of H.
Yeah, that's right. You can.
Casimir, which you write is a Casimir of G.
This is the Casimir of G, yeah. Right? Okay. No, I corrected that. So again, I mean, yeah, I don't think I have more to say about that. Good? Okay. So that's the result. Maybe I have time for one comment on this, because I think this is related to an interesting problem. Do I have? So 15 minutes, let me think. Yeah, I think let me make one comment on kind of an open problem that I think would be interesting to address. It also addresses one of the questions that we had before. So since we were claiming that we've now given the anomalous dimension, one-loop anomalous dimension for all the fields, we can actually write down the one-loop partition function because all the information is there. So, and so the one-loop partition function for states that have finite energy or finite dimension at infinite coupling, or zero coupling in the sigma model, infinite radius, in G mod H, would then take the following form. It's a huge sum over all these things that are in lambda. And so you have, so actually what one does is one computes the partition function as a function of QQ bar. So that's the worldsheet variables, and then the things that are raised to L0 and L0 bar. And then X, which is an element in the Cartan torus of the symmetry, which is an element in the Cartan torus of G. Okay? So it's kind of a specialized, unspecialized partition function. So you get a character of a representation of G So sum over all the representations that appear in your model. Then you get branchings of, this ends our branching number of a representation of G into representations of H. This kind of counts basically the sections in your homogeneous vector bundle. So it's basically counting these zero modes. Then you get some functions B mu Q, which I guess in simple cases are sort of related to theory of sure functions and stuff. That just counts sort of these P mu's that you can build. And then you also need the diffusion rules, so the number of these D's that you can have. So that would be a formula for the partition function at zero coupling, okay? Just counting all the elements in this thing. And so now coming back to one of the questions, in cases where you have sufficient control over all this representation theoretic data, you can actually sum up this thing and express it in terms of infinite products, which you can directly identify as just the partition function of the sigma model, okay, and also express in terms of theta functions. So you see then this way that you have really correctly counted all the fields of the theory. So now this formula gets deformed, of course, at one loop by what we just computed by this P. So this would be the expression for the one loop partition function. And so one interesting issue, I guess, is, I mean, I told you before, without this piece you can study, I mean, this is a conformal field theory, so I guess you're immediately tempted to think about modular invariance. And so without this piece, of course, I told you that you can have an infinite product representation, which you can express in terms of theta functions. But once you insert this piece, of course, it's not so clear what happens under modular invariance. And I think there's sort of an interesting, I don't know how to call this really. I mean, Mike Douglas was thinking about modular invariance as in these one-loop partition functions for sigma models for a while, and suggested that there should be some relation with trace formulas. Of course, somehow in modular invariance usually works as a sort of relation between momentum and winding modes. And of course, the momentum modes that we looked at here, they have some relation, of course, with the Laplace operator. So they kind of, I mean, their contributions to the normal dimension depend on the Laplace operator. The winding modes, of course, should then give, I mean, have some contribution from the length of winding modes. So it smells a little bit like trace formula type relation that you need for modular invariance. So I don't quite know what the story is here. Of course, this is just a spectrum for momentum modes. By definition, these were all the modes that had finite dimension at infinite coupling. So I mean, the issue of modular invariance of this one loop partition function.
Like a heat kernel type formula.
Yes, it is. Yeah, it is. Yeah. So I don't have much more to say about it, but I think it might be interesting. I also don't know anything about trace formulas in superspaces. I haven't found any mathematical literature on that. But this might be sort of a more well-defined framework to actually test some of these ideas. Anyway, since I'm a little rushed in time, let me leave it with that. And so that concludes what I wanted to tell you about sigma models, okay?
But it has to be modular covariant, right?
Well, I mean, there could be winding modes coming in. Of course, geometrically, you would wonder why winding modes, for instance, on a three-sphere with two fermionic directions. But so I'll come back to this issue in a bit, yeah. In the next 10 minutes, by definition. So there could be winding modes which we don't see here in this expression, but would have to be there for modular invariance as soon as we go to infinity.
Means that you have to add the
Things that leave the spectrum when you send R to infinity, right? So I'll come back to this if I have time, if you don't ask too many questions now. Okay. So this was what I wanted to tell you about sigma models, okay? And that's sort of the main result here is this. I should actually say, so there's a slight modification if you discuss models with running coupling. You can modify this formula, and then you can also compare with the expressions, in particular by Franz Wegner, who computed these things for ON models in particular, and that's the same result. But this formula here is actually completely general. It applies to all these models that I put on the blackboard before. Okay. So, any questions? Okay.
Is there a stupid question. Is there a contribution to, so this is anomalous dimension?
Yes.
Is there such thing as anomalous spin?
No, this is no. It's just really. I mean, the H and H bar are deformed in the same way. Okay. So let me come to the third part. When I started this, I said that somehow restricting to the class of sigma models, when you discuss any kind of conformal field theories, in particular non-unitary ones, is not a smart choice, because somehow you won't understand the space of models very well. I mean, you know all when you study, for instance, CP1 model with theta angle pi, it flows to the SU2 Wess-Amino model at level 1, which is not directly a sigma model. Or other examples would be the massless Turing model, for instance, which is written in terms of dimension 1/2 fermions, which is also not a sigma model, but still we know it's related to a free boson theory, which is a sigma model. So somehow it's not a good idea to just restrict to this class of models if you want to understand the spaces. So let me take that as a motivation to think about a little bit about Wess-Amino-Novikov-Witten models and duality. So the way the Wess-Amino-Novikov-Witten models will enter is actually through a generalization of the Turing model. So generalization of the massless Turing model is the Gros-Neveu model. And so of course there's also a OSP version of a Gros-Neveu model. So the way you build that is as follows. So now you have as fundamental degrees of freedom not dimension 0 fields X like we had a long time ago, but you have dimension 1/2 vectors. And so you have an action of this type, and now I can write terms with only one derivative as I wanted to do before. So this would be, so again, this is with the metric eta, this contraction. So this is a model that one would write down as called an OSP Gros-Neveu model if psi here is an object of dimension 1/2 that sits in the vector representation of OSP representation. Now, again, if OSP was just O2, then this is just a standard massless Turing model with a 4 fermion interaction, and we know from bosonization that it's the same as the O2 sigma model that I talked, the free field theory. And in fact, there has been a conjecture around that this relation extends to the OSP case, to these conformal OSP models. And so it was conjectured that this Gros-Neveu model, OSP 2n plus 2n Gros-Neveu, is dual to the OSP, let's say, S2n plus 1 2n sigma model. Okay? So again, if n is equal to 0, then this is just the free, so the massless Turing model, and this will just be an S1 free boson. Now, of course, that's a very non-perturbative duality, because so this coupling G here is related, of course, to the radius, and the radius, infinite radius, corresponds to a large value of G, or non-zero value of G. So somehow it's a non-perturbative duality. Of course, for the free boson, because everything is free, you can easily change your variables, and then you can make this relation manifest. But of course, in these non-interacting theories, won't be quite as easy. So actually, this was initially conjectured by Candu and Saleur, and then we worked very hard to kind of see evidence for this duality. In particular, there was a nice lattice study. So you can put this model, you can introduce some kind of OSP Heisenberg spin chain and then study that numerically and look at the low energy spectrum. And you will actually see that that there is actually a marginal coupling that you can tune, and that in certain value for the coupling, you see actually sort of this Gros-Neveu spectrum, and in other values you see the sigma model spectrum. So this was just purely numerical evidence. Also, you had to put the theory for that on the boundary, on an interval with certain boundary conditions for this to work, because otherwise the spectrum just looked too complicated.
The spin chain is non-relativistic.
The spin chain is relativistic, yeah.
Is it relativistic?
Yeah, so spin chain is relativistic. So it's a Heisenberg. It's just the OSP version of a Heisenberg spin chain. Non-relativistic.
It's non-relativistic. It's surprising that it mimics this system.
Yeah, but I mean, again, this is so it's just like the Heisenberg, I mean, this kind of XXZ model, right? I mean, that kind of mimics the, I mean, you can see sort of the Turing and the O2 model, right? So this is the high model. It's kind of surprising, yeah. I mean, it was not obvious that it would work, but it works. Sorry? Yeah, this is a critical model. That's of course.
But this is massless, so this is supposed to be conformal.
Yeah, so this describes the low energy degrees of freedom of that spin chain. So it's critical, yes, of course. I mean, that's what I'm saying. And on lattice, you can see that in the numerics, you can see that we make the lattice larger and larger, and eventually the spectrum will just kind of stabilize and just, yeah. So then later also we kind of gave some analytical nice interpolation, but it was all difficult. And mostly I think because, restricted to the boundary. So now this actually can be thought of as a Wess-Zumino model. You can think of this theory, these free fermions you can use to build an OSP 2n plus 2 2n Wess-Zumino model at level 1. It's like one of these free fermion constructions. So this is like an OSP 2n plus 2 2n Wess-Zumino Novikov-Witten model at k equal to 1 plus, and then this term that's quadratic in the fermions you can write as a current-current interaction, where these are now the currents, holomorphic currents of the Wess-Zumino model. Okay, so I wrote them with capital JJ bar. Okay, so it's a current-current deformation, and here you sum over all degrees of freedom, all the directions in G. Okay, so this model here, of course, has a the Wess-Zumino model at G equals 0 has a G left and G right symmetry. So this has a G left times G right symmetry. And then this interaction here, of course, breaks that because you contract an index from the left, an index on the right. It breaks that to the diagonal. Okay, that gets broken to the G diagonal. So ultimately, of course, there's only one global diagonal symmetry left. And in fact, of course, as soon as you turn on the perturbation, there's also no current algebra left. So it's just a global symmetry. And the J's are then, of course, the conserved charges, but they are also no longer holomorphic once you go away. So this motivated us to look at deformations of Wess-Zumino model, and our results are slightly more general than this. So we said, okay. So this is the second result on the almost. Okay, we have a bunch of results, but I'll give only one that we'll need here. Turned out that for some fields in this theory, we could actually give an all-loop expression for the anomalous dimension. And these are fields which transform in what's called a maximally atypical representation. Now, if you don't know much about superalgebras, that may not tell you much, but you know in most representations, of course, bosonic and fermionic degrees of freedom are just balanced. You have the same number of bosonic and fermionic degrees of freedom. But then there are some representations of superalgebras where you have an excess of bosons or fermions, and these are called maximally atypical. And for those guys, we can actually write down an all-loop formula for the anomalous dimension. And So in fact, for all those representations that are maximally atypical with respect to the diagonal symmetry, okay? So this actually turns out it's a very rich class of such for fields in maximally atypical rep of GD. We can write down a formula for the anomalous dimension. So this is now in the Wess-Zumino Novikov-Witten model at coupling G. So this is an all-loop formula. So the labels, it's labeled by three representations: the representation for the left, the right, and the diagonal representation. The labels come, of course, from the unperturbed theory. That's what you use. Yeah, I can see the sign. So can I have 5 minutes, or is that okay? Good. So the formula, which I won't bother looking at my notes, is therefore going to be wrong, but it's something like this. So that now it's all G Casimirs because there's no H. So this is meant to be an all-loop formula for this particular class of operators, okay? So K is the level of the Wess-Domino model. So this is general. If you just apply it to this model that we have here, you set K equal to 1, and then this formula applies. Okay, so this is the second result. So now in the remaining 4 minutes, sorry, I should have tried a little higher, I'll show you an application of this result. Because again, I mean, this is an all-loop formula. And so if there's a duality, then we should understand what happens to states in the Wess-Domino model. In particular, we could be very ambitious to try to see the zero modes of the sigma model emerging from this formula, right? The sigma model, of course, is infinitely many zero modes, so an infinite dimension space of dimension 0 operators, which are the basic fields that we start with. And the Wess-Domino model, of course, has only one such field, and all others have high energy. But of course, once you turn on the perturbation, I mean, some of them will come down, and that should be described by this formula, at least for some of the operators. And you could try to find these operators that have zero energy at infinite coupling. So now I have to, because I have run out of time, so let me just give you a rough sketch of how that goes and point out 1 or 2 little amusing facts that make this possible. So it turns out that duality is between this deformed Wess-Domino model and the supersphere model when you identify G is equal to 4 minus R squared over 4 plus R squared. So G equal minus 1 is the point that would correspond in the moduli space of the deformed Gros-Neveu model to the sigma model. And you can write down this formula that I had on the previous blackboard. You can write this down in the vicinity of this G equal minus 1 point. Just look at the leading and the next to leading contribution, and you will find that it takes the following form. It's minus 1/2 Casimir left plus Casimir right, GG, plus 1 over R squared Casimir dg. So that's the formula plus corrections, of course. This is only the leading terms written in terms of R. So, and I've replaced the G in the formula before by R to this formula, and then expanded the leading contribution. The next one would be 1 over R to the 4th, and also set K equal to 1. So this is what you get. So in order to make this look like something that we saw in the sigma model, and zero modes in the sigma model, of course, this piece would have to be 0. So we have to find whether there are states where this thing here is cancelled. So of course, this is just a shift of the dimension, right? So in the Wess-Domino model, they start usually at some higher dimension, and then the shift is this. And of course, this piece here, which is negative, could get like negative dimension states and stuff like this. But then you kind of look at representations of your OSP current algebra, and I don't know a general, like, simple proof of that, but you just inspect them, and you will find that in these representations, all states have a conformal weight which is larger than 1/2 of the Casimir, okay? So there's a general formula, for instance, when you look at the vacuum representation of the OSP Wess-Domino model at level 1, then you have always H larger or equal to 1/2 C. So this looks a little bit like chiral primaries, but of course here this is a worldsheet quantity, this is a space-time object, right? So it's really, so I don't have a sort of algebraic derivation of that, but it's just by observation. So then you also find that those for which this is satisfied, these are very particular representations. You can, there's only one parameter, I mean one family of such representation with energy dimension 1/2 K squared. So you can list them for which is satisfied. And then for these representations, they will then actually, so then you have to combine left and right movers. And so you tensor these representations, and you actually, I forgot. Okay, so I don't have time. So let me just describe it roughly. You see that that this piece then is cancelled by the anomalous dimension at the Vesumino point, and this piece here is compared with this formula that we had here. And since we are discussing non-derivative operators, this thing is not there, and you see you get exact agreement. So that kind of is an application. Now I see that Peter can't stand it any longer, so I won't tell you more. Sorry for going over time.
Have you considered the more general super sigma models?
So we did worldsheet.
No, I mean the target is just supermanifold.
Target is supermanifold.
Study theory with some metrics.
Yes.
Superspace.
Yes.
And not necessarily homogeneous.
No, I mean, as I said, for non-homogeneous spaces, or for non-homogeneous, no, I mean non-homogeneous, not even. I mean, okay. So because I'm mostly interested in the application to ADS, I mean, then at least that's all still homogeneous, but not symmetric.
Then you would derive super Einstein equations, etc.
Yes, that's right. Yeah, yeah. I mean, I haven't, but probably somebody has looked at perturbative computation of beta function in those cases. I would probably look in. Yeah, I haven't done much about that. Of course, for us, the symmetry is very important. I mean, okay, so the credo is really that if you don't have at least this global supersymmetry, it's global supersymmetry that makes these non-unitary theories treatable somehow. Without the global supersymmetry, I wouldn't know how to do any of this stuff. Unless you have worldsheet supersymmetry, of course, then you're in a different game.
Manifolds with the positional structure, like a vector field which goes to zero, for example. Human.
Yes, then you can probably derive some results on particular subsectors, I guess, of those models, right? I mean, they would.
For you here, the global supersymmetries. Oh, you mean you have more than just one vector field?
Yes, yes.